Okay, so welcome back, everybody. So let me just give you a recap of where we ended off last time. So we were discussing SL2 irreducible representations, and we proved the theorem that classified all of these, okay, up to isomorphism, up to this notion of intertwining isomorphism that we'll review again later. So the statement is that all SL2C irreducible representations, IRREPs, are given as follows. They are given by these vector spaces that we denoted by the symmetric mth power of the standard representation C2. Okay, so this M is any non-negative integer. Okay, so how do we? So it's a nice result that despite this complexity of these irreducible representations, right? Everything is just determined by a non-negative integer. Okay, and of course, there's a lot behind this, but the nice thing is that we have this nice classification result now. Okay, all IRREPs look like this. All SL2 IRREPs look like this. If you want to construct this explicitly, here's the model how we presented it last time. So for this vector space SMC2, first of all, I'll take a basis in C2 that I'm going to call X and Y. Okay, so instead of the usual notation, say E1 for the first vector 1, 0, I'm going to call it X. And for the second one, E2, I'm going to call it Y. Okay, so that's the basis on C2. And then I'm going to start taking symmetric expressions, symmetric tensor products in these expressions. And here's a basis for this space. Okay, but moreover, this, what I've written down here, this is actually a so-called weight basis. Okay, this is a nice basis with respect to this nice operator H. Okay, and this, so these guys are eigenvectors for the action of H. Okay, so where the eigenvalue is m minus 2, m minus 4. Okay, always lowering by 2 all the way down to the lowest one being minus m. Okay, so these are the so-called weights. Okay. Just to be explicit, right? The action is determined by these operators here. So if you're going to write it out in the m is equal to 4 case, then here's what it looks like. Okay, so you're going to have an upper triangular matrix here. Okay, oops. And then zeros elsewhere. In this case, you're going to have, it's going to be nice and diagonal. Highest weight is 4. And then on the diagonal, it just keeps lowering by 2. And then lastly, well, we're going to have a lower triangular matrix. Four, 3, 2, 1. And the rest all zeros. Okay. So these are expressions for these guys, okay, in this basis. So make sure you're able to verify that. Okay. When we first introduced the SL2 action on symmetric tensors, we actually put a symmetric, so SMC2 star, and we wrote down analogous matrices there. Those are actually, they look a little bit different. So if you compare those matrices with these matrices over here, then they're negative transposes of each other. And that's because we had an extra dual on this C2. Okay. So what I want to do in this first hour now, after this little recap, is I'm going to review a little bit on dual spaces. I want to make this identification, at least in the SL2 case, between C2 and C2 star, the dual vector space. What is this explicitly? Okay. Well, we use some of that later on, but I want to be really concrete here that in this case, there is an isomorphism between C2 and C2 dual. Okay. Then we'll talk a little bit more about irreducible representations, in particular this result called Schur's lemma. And then probably in the second hour, we'll get to a lot more about SL2. Okay, so so-called Clebsch-Gordan theory. Okay, so let's do a little bit of a review of dual spaces. Okay, so recall that's the following. So given a representation, we can induce the so-called dual representation, okay, on the dual vector space consisting of linear functionals on the original vector space. So the dual rep is given by this representation on V star. And how is it described in terms of the original this given representation pi? Okay, so to a G, I need to tell you what is pi star G. Okay. So what that is I take G inverse and give it a transpose. Okay, so pi of G inverse is like a matrix acting on this space over here. If I fix a basis over there, and then I take its transpose. Okay, so right, so there's this inverse and then transpose to construct the corresponding matrices for this dual representation. So that's for the group. At the Lie algebra level, how do you construct these? Well, just like you usually do, to get from the Lie group to the Lie algebra, you take curves through the identity and then differentiate them at the identity. Okay, so how does this dual representation for the Lie algebra work? Okay, so we're going to define a representation on V star. Okay, and what that does is, well, if you take a curve like G of t over here, okay, so I'm going to differentiate this expression at the identity. And what I'm going to get is the following. Instead of inverse transpose like you have in the group case, you're going to get negative. And then you take the original representation, apply it to X, and then take the transpose of that. Okay. So we'll see this in the concrete example of SL2. Okay, but just let me do a little bit of review here. And I think Erwin probably also stated some results like this. So at the group level, so pi star, this dual representation, is irreducible if and only if pi is irreducible. And pi star is isomorphic to pi. Okay, so I'm always going to be working with finite dimensional representations. Okay, so let's assume finite dimensional vector space. Okay. So at the vector space level, we have V star is isomorphic to V. Okay, but this is saying at the representation level, which consists of V plus this extra homomorphism. So then at that level, these guys are isomorphic. Okay, so you might have to review a little bit on dual spaces here, but it's a well-known fact that with V being finite dimensional, then if you take the double dual, then this is isomorphic to the original vector space. Okay, so try to make that explicit if you're not used to working with dual spaces. Okay, and then we have the analogous. So now I guess for Let me review this notion also of intertwining, okay, because we want to make precise that C2 and C2 dual are isomorphic, but what does that mean? So let's take a representation, take another representation. Let's suppose these are G-reps. So what's an intertwiner? So then this guy, well, a linear such map, is an intertwiner if for any group element, and any element in the vector space, the following diagram commutes. Okay, so I take V, I hit it with phi, or so hit it with phi, and then I follow it up with the group acting. Okay, so, or I start out in V, and then I hit it with the group element, and then I follow it up with phi. Okay, so for any A and for any, okay, sorry, let's not put this. Okay, so this diagram commutes. Okay, so in other words, okay, if I suppress the pi and sigma notation, what it's saying is that I act first with A, then follow it up with phi. So that's the same thing as you hit it with phi first and then hit it with A. Okay, so for all okay. So the action is mimicked on the V side and the W side. Okay. Rather, it's mimicked in the invertible case, but so if B is invertible, okay, as a linear map, okay, we say phi is an isomorphism. Okay. And again, analogous for linear algebras. Okay. Just to get you guys used to the language of tensor products as well. So if I have any linear map, right, I could view that as an element of a certain tensor product space. So let me just get this down. And what does it mean to be an intertwiner in this language? Okay, so any linear map can be viewed as an element in a tensor product space. Okay. Namely, so this guy accepts as input a V, a little v in capital V, and it spits out something in capital W. And in the same way, so if I could feed something to this object from V, there's a pairing, a natural pairing from V star between V star and V, right? It's just evaluation. Okay, so you feed this something in capital V, you pair it with this piece, and it spits out something over here. Okay, so any linear map lives in this space, okay, this tensor product space. So, well, we talked, we have seen the action induced on a tensor product. We've been talking about that for SL2 on the symmetric tensor products. Okay, you just induce the representation on each factor, okay, at the same time at the group level. Okay, so but when viewed this way, there's another way of writing down that action. Okay, so how do you write it down? The induced representation on this space, or viewed as a linear map, okay, is the following. So phi, okay, if I'm hitting it with an A, a group element, okay, it's going to give me another linear map. So I need to define for you what is this thing on this side. What does this dot here mean? What is the action? Okay. So where A dot phi, well, to define it as a linear map, I have to feed it some input. And you do the natural thing, okay? So on the V side, I have an action. On the W side, I also have an action. So what I'm going to do is I'm going to put an A acting on output values, but I'm also going to twist it with an A on the inside, or rather an A inverse acting on the input. Okay. So these dots, right, mean different things. This is dots. This is the action on a linear map. Here, this is the action on the vector space V, in particular, a vector in that vector space V. Here, it's the dot on the W side, okay, on the output. So on all of this. Okay, so just to be very clear, it's acting on this vector, okay, in W. Okay, so that's an action. And so what does it mean to be an intertwiner? From this point of view, then phi is an intertwiner if and only if A dot phi is phi, okay, for all in G, right? Why? Because it's, let me just expand this a little bit. Okay, so let's just use this formula over here. Okay, so A dot phi equals phi. And this is A dot phi is B. Okay. I'm just going to replace this whole input by some V tilde. Okay, so you have A dot phi V tilde is equal to. So V tilde is this A inverse V. So that means V is A V tilde. Okay. Which is the condition that we had above. Okay. This condition over here. Okay, so phi in this language is saying that phi is an invariant tensor. Okay. So okay, so invariant tensors are going to be important. Okay. So okay, so let's go to SL2 now and make explicit this this correspondence between C2 and C2 dual. Okay, so this is something very special to SL2. I mean, it will also be true for other groups like the orthogonal groups or the symplectic groups. Okay, but and we'll see why later. But it's not going to be true for SL3 and the higher SLs. Okay, so generally a grep pi is not equivalent to pi star. Okay. But for SL2C, okay, we have the following. Okay, so for standard rep, that's a pi, SL2C, acting on C2, we have pi star equal to pi. Okay, so and hence at the Lie algebra level as well. SL2C. Okay, so let's be explicit about this. Okay, so just because we're going to use this intertwiner here later on. Okay, so we have a standard basis. okay, on C2. Okay, it's a dual basis beta star. And one convention is just to raise your indices. Now remember what this means, this dual basis. Okay, these are linear functionals on the original vector space. Okay, so dual basis means that when you pair this, when you evaluate this guy on this guy, it's 1. When you evaluate this on this, it's 0. When you evaluate this on this, it's 0. When you evaluate this on this, it's 1. Okay, so we have EI evaluated on EJ is a Kronecker delta. Okay, so let's take a matrix. So A, B, C, D. Okay, so in SL2C. Okay, so that defines the standard representation. Okay, so for the dual rep. Okay, so pi star SL2C and 2GL C2 dual. Okay, so pi star on A, I'm writing this matrix out with respect to the dual basis. Okay, by definition, I should be taking this A inverse with respect to the basis on C2, the original vector space, and I'm taking its transpose. Okay, so I'm taking this capital A with coefficients A, B, C, D. I'm taking its inverse, so this, and I'm supposed to divide by the determinant, but the determinant is 1 in this case. And then I'm supposed to take the transpose of it. Okay. So remember, so what does this mean in terms of the action on the vector space? Okay, so just to be really explicit, it means that right, so the columns describe the action on the corresponding basis vectors. So A on E1 is AE1 plus CE2. AE2, capital AE2 is BE1 plus DE2. And on the dual space level, this is saying DE1 minus DE2, and A on E2 is minus CE1 plus A2. Okay. All right. So that's how the representation on the dual vector space looks like. And so the claim now is that there's an intertwining. Okay. So basically, what I want to do is I want to line up the bases on the vector space C2 and the vector space C2 dual, create this map such that the action on one gets mimicked on the other side. Okay, so what is this map going to be? Okay, we're going to call this intertwiner tau. We're going from C2 to C2 dual. So it's going to do the following. It's going to take E1 subscript to E superscript 2, and E2, it's going to map to E minus E superscript 1. Okay. And so you could check, so let A in SL2C as above. Then you could check that this satisfies the intertwining condition. And just check it on a basis. Okay, these are linear maps, so it's sufficient to check it on a basis. Okay. So I'll leave that checked in. Okay. So a tau is intertwiner. It's clearly going to be an isomorphism, right? It's trajective and injective. Okay, linear map. So this is an intertwiner isomorphism. And so it's isomorphic to this. Oop, ugh. Pi is isomorphic to pi star. Okay. Questions on that? Okay, a little bit of a notation that we're going to use later on. We're going to come back to. Okay, so again, I like using this XY notation on C2. Okay, so I'm going to use X and Y for E1 and E2. And for the dual basis, this is notation. Okay, so I'm going to call these partial X and partial Y. Okay, so the notation is there, but really you should understand what it means. This is just denoting the dual basis. Okay. But why is it a natural notation? Well, because if I just turn off my brain and just let this act as a differential operator, so it differentiates this first one to be 1, it differentiates the second one to be 0, and vice versa. This on this is 0, this on this is 1. So it's satisfying this Kronecker delta condition. Okay, so we're going to use this notation later on, and just to emphasize, so this tau above is given by, so X goes to partial Y, and then Y goes to minus partial X. Okay. I mentioned above that's right. Invariant tensors are important, and there's one in the background of this of these ideas that I just presented here. Okay, so a little exercise. Okay, so show that the tensor on C2 given by the following. Okay, so capital, superscript, so E1 wedge E2. Okay, so this is a wedge, so it's a skew symmetric combination of tensor products here. Okay, so just as a definition, it's this guy. I'm not putting a half out front as a factor around this for my skew symmetric tensor products. It's a convention, okay, but yeah, it happens to be useful when we're doing insertions and stuff like that, evaluations. Okay, otherwise you would have these extra halves floating around. Okay, so this guy is SL2C invariant. Okay, in other words, A acting on this is itself. Okay, so for all. Okay. So there's an invariant tensor lurking around. This intertwiner that we have here, let me highlight that. It's, oops. Okay, so moreover, verify that this tau, so not expressed in a basis, but as a general linear map, it is obtained simply by taking this omega and inserting given vector into the first slot of omega. Okay. So there's a natural way of building this tau, this natural intertwiner, from this invariant tensor. Okay. So that's a little bit on SL2. We'll get back to it in a big way later on. Okay. I want to focus on irreducible representations now, and so-called Schur's lemma. Okay, so working with irreducible representations is actually quite a strong condition. Okay, so let me state the lemma for sure. Okay, so let's take G irreps, okay? Or at the Lie algebra level, that's fine as well. Okay, so three statements here. Okay, so first statement is that let's suppose that we have an intertwiner. Okay, between two G irreps. Okay. So these could be complicated, right? But the statement here is that there's only two possibilities. Okay, at least descriptively here. So either tau is 0, or it's an isomorphism. Okay, can't have anything in between. Second statement. Let's suppose that V is complex, and being complex, that's important here. Suppose that I look at the self-intertwiners. Okay, so intertwiners from V to V. So then, again, very restrictive. There's only one possibility. Well, this is infinitely many, but in a very controlled way. It's you take the identity map, that's one possibility, or any multiple of the identity map. That's it. Okay. What if both V and W are complex vector spaces? Suppose I have two intertwiners, so tau1 and tau2. And let's suppose they're non-trivial, okay, so non-zero intertwiners. Then we're going to piggyback off of the second statement to get the following, that one has to be, well, a multiple of the other. Okay, so that's so three statements there. Proofs are all quite short, and really just emphasizing these notions of what does irreducible mean? What does invariant subspace mean? Okay. Okay, so the question is, where does this complex assumption come into play? Okay, so we'll see that shortly. Okay, so let's go ahead and prove this. Again, it's all quite short, so let's just follow our nose here. So let's look at the first one. So I have an intertwiner between V and W. Okay, so it's natural to look at some invariant subspaces. Okay, so what's a natural invariant subspace that you could look at? Well, the kernel of that map. Okay, so proof. Okay, so the kernel of tau is an invariant subspace. Prove it for yourself if you haven't done so already. Okay, but let me just move on here. Since it's an invariant subspace, well, remember, V is an irreducible representation. What does that mean? It means that the only invariant subspaces inside V are 0 or the whole thing. So by irreducibility, so either it's 0. Oh, okay, let's do the full thing first. Okay. If the kernel is the whole thing, that's saying that tau is the 0 map. Okay. Or the kernel is 0, but that's telling us that tau is 1 to 1. Okay. We could also look at in this case, the image. Okay, so the image is also an invariant subspace. Okay. So once again, well, W is irreducible. So that tells us that the image is either 0. So image is equal to 0. Okay. So tau is 0. Or the image is the whole thing. Okay. So in this case, so it would be surjective, but we know it's also injective, so therefore you get an isomorphism. And that's it. Okay, so that's the first one. Pretty easy. Okay, just looking at invariant subspaces. Okay, so the second statement, let's just go up. And what was the second statement again? So this says that when we're looking at a complex vector space and an intertwiner on it, okay, then, well, it's just a multiple of the identity. Okay, so over C, remember this nice thing about C is that when you have a linear map on a complex vector space and a linear operator, okay, then we know it always has an eigenvalue. Okay, we've seen this used in the SL2 discussion earlier when we were classifying things. So over C, we know that tau has an eigenvalue. Okay, so that's a nice thing to see. Okay, so again, we want to use irreducibility, so we have to come up with some. It's natural to come up with some invariant subspaces. What's a natural invariant subspace? Well, the eigenspace associated to lambda. So let U be those vectors that are, it's the eigenspace associated to lambda. And this is non-zero because lambda is an eigenvalue. Okay, so B, the corresponding eigenspace. Okay, so then, okay, so if I look at a vector, so then U. Okay, so tau is an intertwiner, so this is the same thing. I could push the A past the tau. This is an eigenvector, right? This V is living inside this capital U. So we have A acting on lambda V. Lambda is a scalar, so I could just pull that out of the linear map out front. Okay, so what did we just show? So if I start out with a vector in U and I apply A to it, then this guy under tau just gets into a multiple of itself. Okay. So that means that, well, so therefore, A on V is also in U, right? Because U is defined by those vectors such that t on that vector, tau on that vector is just this lambda times that vector. Okay. So therefore, U is invariant. Okay, but it's an invariant subspace of V. It's not zero, so therefore it has to be the full thing by irreducibility. Okay. So therefore, by irreducibility. Everybody okay? Questions? Let's finish up the last one. Okay, so let's look at the statement again. V and W are complex. You have tau1, tau2, non-zero intertwiners. Okay. So by the first result over here, right? So either tau 0 or tau is an isomorphism. So these guys have to be isomorphisms by 1. Okay, so let's write that down. So tau1 and tau2 are non-zero intertwiners, so they're isomorphisms. Okay. So they're going from V to W. Okay, so I can consider the inverse, tau1 composed tau2 inverse. Sorry, that's going from W to, okay, so let's try this again. Okay. We want a map on V, right? Yeah. Okay, so this guy from V to V is non-zero intertwiner. So therefore, this is a multiple times the identity line 2. Okay, so therefore tau1 is lambda tau2. Okay, and we're done. Okay, so that's Schur's lemma, and it tends to come up again and again. It's about the structure of these intertwiners on irreducible representations. Okay, quite constrained, especially in the complex case. Okay, couple short corollaries of this. Okay, so let's IV be a complex G irrep or at the Lie algebra level. Okay. If you have something in the center of G, okay, so those elements that commute with everything in capital G, then when this acts on this irreducible representation V, it's quite constrained. Okay, namely, it's just a multiple of the identity. And similarly for G. Okay, so again, this is pretty straightforward. Okay, so yeah, but it's a story about intertwiners, so we have to get ourselves a candidate intertwiner. Okay, so let's take a element of the center, and so claim that if we take A and hit it with this representation, okay, so this linear map, that's an intertwiner. Okay. So let's just double check this. Okay, so let's take any B element of G. And so we want to check is that basically this A and this B, they commute. Okay, so pi of A, pi B. Well, use the homomorphism condition. Okay, so this is pi AB. But A commutes with everything in G, so I could rewrite this as pi BA. Use the homomorphism condition again. So that's pi of B, pi of A. Okay. So we just verified that phi is intertwiner. Okay, so this is an intertwiner on a complex irreducible representation. So therefore, by Schur's lemma. Okay, so therefore, Schur implies that Schur part 2. Implies the result. Okay, it's just the multiple of the identity. Okay, so I mean, we're going to spend a lot of time. Oh, yeah, let me just do a couple more things and then we'll wrap up and take a break. Okay, so right, so first corollary of this is that so any complex era of an abelian guy is one-dimensional. Okay, right, because under any representation, right, we know from this what we just showed that it's just a multiple of the identity map. Okay, so the identity map has lots of invariant subspaces. So they're only going to be, if you want it to be an irreducible representation, so only the trivial invariant subspace or the whole thing has to be one-dimensional. Okay, it's very important that you have this complex hypothesis in here. So let me just state this thing. Okay, so let's suppose I'm working over the reals. And let's take a two-dimensional real vector space. Okay, so then here's a representation. So a two-dimensional representation. So two-dimensional irreducible representation given by G of X. Okay. Okay, so having this complex hypothesis in the above statement here is important to force this one-dimensionality. Okay. All right, sorry, went a little over time, so let's take a break and meet up in about 10 minutes. Okay, so we ended up with this little corollary that any complex irreducible representation of an abelian guy is one-dimensional. Okay, that doesn't, yeah, okay, actually, oops. I shouldn't. There we go. All right, so this is actually a special case of a much more general theorem. Okay, I'm going to quote the general theorem first, just so that you're aware of it, and then I'll deduce the corollary that's more general. Okay, so in fact, star arises from general theorem. Okay, So I'm going to put the proof in the notes in the appendix. Okay. So instead of talking about abelian guys, let's talk about solvable guys. Okay, so there's an important theorem called Lee's theorem. So let V be complex and, as usual, finite dimensional. And let's take a matrix Lie algebra. Suppose that it's solvable. Okay, so then. Okay, so V contains a common eigenvector for all of G. So what does that mean? There exists a non-zero vector such that when I act by an element in G, then it just rescales the original vector. But of course, this scalar could depend on the input x. Okay, so really, I have some functional here. And this idea of these functionals coming up as eigenvalues is going to come up in the semi-simple case in a big way later on. Okay, so V has a common eigenvector. And the second statement is there exists a G invariant flag in V. What do I mean by flag? Basically, a flag is a nested chain of increasing subspaces. Okay. Another way of phrasing this is there exists some nice adapted basis such that in this basis, G can be viewed as sitting inside upper triangular matrices. Okay. So basically, G has this kind of, at least in this way of representing it, it has this kind of block shape. Okay, so you have some stuff that you don't know of over here, but then a bunch of zeros like that. Okay, so this flag is, so if I view the basis as E1, E2, etc., then it's saying that, okay, so I have this nested chain of subspace. This sitting inside, this sitting inside, this, etc., but such that each of these subspaces are invariant under the action of G. Okay, that's what really is going on when you're saying you're working with an invariant subspace, right? You have a block in a subblock inside this matrix. Okay. Okay, so that's Lee's theorem. Okay, but this idea of having a common eigenvector, it leads to this corollary that generalizes the one that we stated for the abelian case. So let G be complex, solvable. Then any finite dimensional G Europe is one dimensional. Right? So that comes as a direct consequence of this common eigenvector condition coming from Lee's theorem. Okay. So, I mean, one-dimensional irreducible representations, you might think, okay, well, what can a Lie algebra do to a one-dimensional thing? Well, it could just act by scalars on that one-dimensional vector space, right? So, okay, that's not that interesting. But what this is saying is really that, I mean, irreducible representations really are not like really we want to the goal is to describe like all representations, right? And in nice conditions, under nice conditions, you have this complete reducibility property that you could split apart any representation into a direct sum of irreducibles. Okay. But for solvables, you don't in general have this complete reducibility property, and irreducible representations are relatively not so interesting. They're important, but they're not as like there's a lot more complexity to the solvable cases, right? I mean, if I just take upper triangular matrices, you can see there is some complexity in there. This does define a representation, okay? And the size of the blocks might be quite different, right? Just there's a lot more complexity associated with general solvables. Okay, irreducibles are not going to be sufficient to describe all, or direct sums of irreducibles are not going to be sufficient to describe all representations of solvables. Okay. So, anyways, we're going to be concentrating more on the semi-simple case, and we've done a fair bit so far. This theorem of highest weight for SL2. So what we're going to turn now to is this Clebsch-Gordan theory. Okay, so as I said, so any finite dimensional SL2C representation is completely reducible. So we could ask so-called. So it goes by this weird name called plectism. Okay, so if I start taking tensor products of irreducibles, say of SL2, okay, in general, that's not going to be irreducible. So, okay, what is the decomposition into irreducibles of this more complicated object that you're building up from simpler objects? Okay, so what is the decomposition? Okay. Into irreps of, say, let's take a tensor product, or let's take a symmetric tensor product, or let's take a wedge product. Okay, of course, you could deal with higher tensor products as well, or higher symmetric products, higher wedge products. Okay, so the key idea, okay, just like in the classification that we had before, so key ideas, use H. Okay, that's really the main idea. Okay, we're going to see this, how to do this now. Several examples. Let me just remind you that at the Lie algebra level, if you're acting on a tensor product, okay, how is the action going to be realized? I'll remind you. Okay, but here's an important point. Weights on a tensor product, okay, will add. Okay. What do I mean there? So let's suppose I'm going to take a tensor product of two weight vectors for H. Okay, so suppose HU is lambda U, and HV is, let's use a different eigenvalue, mu V. Okay, so let's take H acting on the tensor product. Remember what it means for a Lie algebra action on a tensor product. You let the element act on the first factor, keep the second factor the same, plus keep the first factor the same, act on the second factor. Okay, as in you have a Leibniz rule. Okay. Okay, well, this first guy is lambda u. Okay, so and the second guy is mu v. So I collect terms together. I have lambda plus mu all times u tensor v. As in, the action on the tensor product is, well, this guy is another, this guy is an eigenvector for H. Okay. And the eigenvalue is going to be lambda plus mu, as in the eigenvalues, the weights will add. Okay. Okay, so let's go through several examples. Okay, so we want to first, like, you could either approach it concretely or abstractly, and it's easier to do it abstractly first. Let's understand what's going on, and then we'll do it in more detail. Okay, keep in mind this theorem of highest weight. Okay, so let's take V2, tensor of V3, and let's decompose it abstractly. And so this starts off by listing the weights for each factor. Okay. Then take all possible sums. Okay, so for V2, what are the V2 weights? Well, it starts out with 2. That's the highest weight, right? That comes from the what we had before in the classification theorem. And then you lower by 2. So 2, 0, and then minus 2, and then you stop. Okay. V3 weights. So 3, 1, minus 1, minus 3. Okay, so now you just start taking all possible sums of these weights. Okay, so I'm going to build a table. Okay, so just start adding them together. Okay, so just fill in the entire table. So inside V2 tensor V3, let's just double check. So V2 has dimension 3. V3 has dimension 4. Okay, so 3 times 4 is 12. And we have here 12 eigenvalues. Okay, all possible sums. So, you know, we have this theorem, so we didn't prove it, but this complete reducibility for SL2, right? So V2 tensor V3 is a direct sum of irreducibles. We know what all irreducibles look like abstractly. They're these VMs. Okay, so you look at this list of eigenvalues, and you start asking the question, what sort of VMs can appear there? And where you always start is you start with the highest one. Okay, we've been calling it the theorem of highest weight. You could also work with lowest weights if you wanted, but we'll work with highest weight. Okay, so what's the highest weight here? It's 5. Okay, now that 5 tells that there exists in this decomposition of V2 tensor V3 a V5. And we know the eigenvalue is there, right? 5, and then you start lowering by 2. So, right. So the highest weight, 5, generates V5, okay, which is dimension 6. Okay, so weights 5, 3, 1, minus 1, minus 3, minus 5. Okay, so we're going to remove these. Okay, so let's just let's start removing. Okay. So it doesn't matter where I'm just viewing this as a list. Okay, so I'm just going to start crossing off some of these eigenvalues. So 5, 3, 1, minus 1, minus 3, minus 5. Okay. Don't pay attention to the exact position of, I mean, there is multiplicity here, right? You have a 3 and a 3 there. Don't pay attention to the position of this in this particular table. Okay, it's just I'm crossing off these eigenvalues as being used as, yeah, they're as in they appear in this abstract V5. Okay. So what we're left with is what's over here. Okay, but again, complete reducibility. Okay, so these eigenvalues correspond to some irreducible, some direct sum of irreducible representations. Start with the highest one. Okay, let's do a different color. Okay, so we have this 3. 3, 1, minus 1, minus 3. Okay. Okay, so we remove the V5 weights.
Sorry, but it was it so that whatever you cross out in the table doesn't really matter as long as you just cross out what is generated.
Yeah, so I mean the fact that so for instance 3 here appears as 2 plus 1, or 3 here appears as 0 plus 3. Okay, I don't want you to pay attention to that. Okay, I just want you to pay on this. I have this list of eigenvalues and I've used some of them up.
Right. Yeah. But I mean, like you start, I mean, when you cross out all the purples one, you crossed out from the left to right and then downwards, but could I in principle just do 5, then 1 down, and then
order doesn't matter. That's the thing that I don't want you to pay attention to.
Yeah, okay. And I just wanted to ask you, just to
Yep, good. Okay, so remove the V5 weights, then repeat. Okay. We get V3, then a V1. Okay. So conclusion. So we have V2 tensor V3 is isomorphic, okay, not just as a vector space, but as a representation of SL2 to a V5, a V3, and a V1. And that's of course through a dimension check. Okay, so we argued before, okay, so 3 times 4, so dimension. Okay, so this is dimension 12. And here, this is dimension 6, dimension 4, dimension 2. Okay, so it all adds up. Okay, questions on that? Okay, so this is an abstract decomposition. Okay, you might want to have something more concrete. Okay, so as in, well, we know that we have this abstract decomposition. If there is a V5, there's a V3 and a V1 sitting inside here. Okay, so natural question is, how are each of these guys realized as actual sub-representations inside here? Okay, as actual subspaces with an action. Okay, so it's a question: how are the irreps on the right-hand side realized as actual subs here, as sub representations inside? Inside. Okay. And the key idea is to go back to the this theorem of highest weight. Okay, so you know that you have this there. In general, generating the entire thing is complicated, but there's the simplest part, namely the highest weight and the highest weight vector. Okay, so to describe a highest weight vector, so that's what I'll do in this next example. Okay, so PID. Okay, it suffices to describe the highest weight vector for each. Okay, this is really important. Okay, because it's gonna, because in general, describing these is very complicated, but there's this simplest part that we're going to be going after. Okay, so let's go V2, V3, explicit decomposition. Okay, so as we know that this V5, right, abstractly, it's an S5C2, okay, with highest weight vector X5. This is abstract, okay. But let's see, from star, this V5 is embedded somehow into this V3. Okay, so we want to describe. Okay, we want to describe this. Okay, so how are we going to describe this? Well, right, this V2 is S2C2. This V3 is S3C2. Okay. Highest weight vectors, X squared and X cubed. Okay. So I want a highest weight vector for this V5. I'm writing this out and this out as these models. Okay, in each case, I have polynomials in xy of degree 2 and of degree 3. Okay, and these are the highest weights, highest weight vectors. Okay, what are the weights? 2 and 3. Okay, so what is a highest weight vector for for this V5 as it sits in there? We can just take the tensor product. Okay, so highest weight vector for V5 as it sits inside V3 is X2 tensor X3. Okay, let's keep the tensor product in there. Okay, just be careful. Okay, so just to illustrate how, I mean, first of all, it's simple, right? You, I mean, we said above that when you take weights associated with tensor products, I mean, the weights add. So we know that this guy, right, it has weight 5. Okay, so this has weight plus 5. And so to describe this V5 entirely, right? This V5 is 6-dimensional. Okay, we just have described the top dimension, top 1 dimension. Okay. So let's be explicit. Let's generate all of V5. How do we do it? Well, you're on the top. Let's apply lowering properties. Okay, what is the lowering operator? It's this guy. And to this highest weight vector. Okay, so let's put this, let's make this really explicit so you get a feel for this. So we have this explicit picture, and then we have abstract picture. I think it did the other way around. Okay, so the abstract picture is going to be just this V5. Okay, so you have x to the 5. Let's apply y to it. So we differentiate. So we have 5 x to the 4, but then you multiply by y, right? We're applying this guy. Okay. You keep going, keep going, keep going, keep going. Okay. Okay, I'm going to be careful. I'm just going to keep all the coefficients there. Okay. I could rescale, but the point is that I want to set up an intertwiner afterwards. So I'm going to do the exact same thing, but now starting on the over here on the right with x2 tensor and x3 is my highest guy. Notice, so on this left side, if I were to do it one more time to here, right, this y, it kills an x and then it adds a y, okay, multiplied by y. So this is the bottom one. So if I hit y again on this, you'll get 0. Okay, and this whole thing, right, is 6-dimensional as you expect. Okay, so now let's do it on the right side, but now in the explicit picture. Okay, inside V2 tensor V3. Okay, again, apply this. How do I apply it on a tensor product? I use Leibniz rule. Okay, so I do it to the first factor on the x squared. I keep the second one the same. And then I keep the first one the same, and then apply it to the second factor. Okay, here I get 3x squared y. I'm going to keep the x squared y over there. I'm going to put the 3 in front. Okay, but we just keep doing this. So I'm just going to write the answer. Okay, and something you have to collect some of the terms together. Okay, you might have some repetition. Okay, so but here is the answer. Right, so as you see, I mean, on the right side here, it does get messy, right? You are working in a complicated tensor product space. And lastly, get that. Okay, and just double check this. Yeah, I think it looks good. Okay. And again, on this bottom one, if I hit it with y again, I'm going to get 0. Okay. So there is a correspondence here. Okay, so I have a particular basis over here. It's a weight basis. So these are all eigenvectors for the action of H. Okay. And you know what the eigenvalues are, right? So it's going to be 5, 3, 1, -1, -3, -5. Same thing over here. These are all eigenvectors, weight vectors, and the eigenvalues are the same. Okay. So this map that I put in pink here, so the map phi sending the basis on the left-hand side to that on the right-hand side. That's an intertwine. Okay. So it's mapping a basis to a basis. So it was an isomorphism. So what we just described is an isomorphism of these representations. Okay. This is V5. Okay, this is V5 as it sits inside V2 tensor V3. This is the explicit realization of that. Okay. So that was the V5, right? And we had two other pieces. So I'm not going to do that. That's a good exercise for you guys. Okay? So to so realize V3 and V1 as sub-representations inside this tensor product. Yeah. And just so that, I mean, it's a little slightly, it's a bit more complicated, but it's not that complicated. But the subtlety is that, let's look at these eigenvalues. Okay, so we want a V3. Okay, notice that there's a two-dimensional eigenspace. Okay, for this eigenvalue plus 3. Right. So question: Can you write down two eigenvectors with eigenvalue 3? Right. So you want to find these two eigenvectors with eigenvalue 3. Take a general linear combination, put some arbitrary coefficients A and B in front, and so we want to figure out which one is going to actually generate this V3, right? So as in, we want to create a highest weight vector for that V3. So what does it mean to be highest weight? It means when you hit it with an X, then you kill it. Okay, that's what it means to be highest. Okay, so that's a little exercise for you. To find what that highest weight vector is for this V3 as it sits inside there. For this V1, well, you can see there's a three-dimensional eigenspace. Same sort of idea. Okay, so you find explicit vectors, a three-dimensional weight 1 subspace over here. Okay, take a general linear combination, hit it with X, and it should be 0. Okay, and that's going to be enough to pin it down. Any questions before I go on? Okay, so we have natural projections, okay, onto these sub-representations. Okay, so for example, you have this V2 tensor V3, which is a direct sum of V5, V3, V1. But you could, because I have a direct sum, I could project. Okay. You could ask to describe these explicitly. Okay, so for instance, over here, how do I take, how do I get from here to over here? Okay, so notice that, so how do I get from here to over here, or say from here to over here? Okay, I mean, notice that we have coefficients here. So 60, 20, 120. Okay, here it's 18, 36, and 6. Okay, but notice that when you add all these up, okay, so 6 plus 36 is 42, plus 18 is 60. Yeah, it's matching up with that. 48 plus 72 added up. Okay, that's 120. Okay, that's no coincidence. So what this map is, well, first of all, yeah. So for instance, over here, so we looked at the coefficients, x squared. But let's look at the product of these two factors. So x squared y times y squared. So it's x squared y cubed. And then we're over here. Same thing over here. xy times xy squared. So you have x squared y cubed. Okay, so this there's going to be a natural projection here. That's basically just symmetrization. Okay, symmetry. When you symmetrize, then it's basically you're forgetting about this explicit tensor product. Okay, you could just push your symbols past each other, and then all these terms collect, all these coefficients collect, and then add up to the result on the left-hand side. Okay, so you have natural projections onto sub-representations. So these are more generally called so-called Clebsch-Gordan pairings. Okay, so I'll describe these in more detail later. Okay, let's do another example. Let's do a symmetric tensor product. Okay, and we're going to start out with the abstract decomposition. Okay, so V2 weights, very familiar, 2, 0, minus 2. Since I'm dealing with S2, okay, symmetric tensor products, what I want to do is not take arbitrary direct sums. What I want to do is take unordered sums of eigenvalues. To get the weights of okay. So again, I'll build a table, but I'm just going to fill in roughly half of the table. Okay, so I have positive 4 here, I have 2 and then 0. Okay, so I'm just going to fill in this one, and this one. Right. So 2 here was obtained as 2 plus 0. Okay, but that's going to be the same as 0 plus 2. So I'm going to forget about this one over here. Okay. Okay, so this guy is dimension 3. Take the second symmetric power is dimension 6, and there's 6 eigenvalues over here. Okay. So, but now that you have this list of eigenvalues, then you follow the same procedure as before. So the highest weight plus 4 generates a V4, so which is dimension 5. So 4, 2, 0, 2, 4. Okay, and then I have just a single 0 left. Okay. All that's remains is single weight 0. Therefore, S2V2 is isomorphic to this, so a copy of V4 and a V0. Okay, so that's our abstract decomposition. And similar exercise as before, but now working in a symmetric tensor product. Okay, so realize V4 as a subrep inside S2 V2. I'm actually going to do the V0 in the next example. But let me just end off with a remark. Okay, the presence of these V0s are extremely important because that tells you that you have an invariant tensor. Okay, invariant tensor sitting inside this space, or rather, we're going to do it slightly different. We're going to actually use the dual, and you're going to see the significance of this. Okay, so. Important. Okay, so what am I saying? Okay. So we have S2 V2 star. Okay, well, that's the same thing as S2 V2. Okay, which is a V4 V0. Technically, like what we showed before is that V1 star is isomorphic to V1. Okay, standard representation and its dual are equivalent. But basically, we're going to induce that intertwiner to all of the higher VMs. So we can, yeah, so basically V2 star is isomorphic to V2. Okay, VM star is isomorphic to VM. Okay, so we have this decomposition for S2 of V2 dual, and this is going to indicate there exists a unique, well, up to scale, SL2C invariant bilinear form, symmetric bilinear form G on V2. Okay, so so that's what we're going to find after the break. Okay, okay. These invariant tensors are important. Okay, so let's continue with where we're at. So the presence of these V0s are very important. Okay, so they indicate the existence of an invariant tensor. Okay, I've just put in this isomorphism here so that I can describe this as a tensor as a form on V2. You don't have, I mean, you could define it as a form if you just forget about this part over here. You could describe this as a tensor on V2 star, but just I don't have that star. I support this for that. Okay, so so we're gonna have this nice symmetric bilinear form that's invariant. So it's like a metric, okay, except we're in a complex case. So you could ask, is it non-degenerate? Is it non-degenerate? Well, you look at the kernel of this bilinear form. How is the kernel of the bilinear form defined? It's those vectors that when you insert into the first slot of your bilinear form, then that is 0. Okay, so this kernel, well, you check, it's an invariant subspace. Okay, SL2 invariant subspace. So irreducibility, it's all of V2. Okay, but this is impossible since G is going to be non-zero. It's a non-zero vector that we're going to pick is spanning this V0. It's either that or it's 0. Okay, so therefore the kernel is 0, so therefore G is non-degenerate. Okay, so notice I know nothing about how G looks like explicitly yet. We're just from the abstract existence of this V0, and using this invariant subspace, irreducibility, we're now concluding that this is necessarily non-degenerate because there's some properties a priori about this this guy. Okay. Okay, but now let's be explicit. Okay, so let's go ahead and try to find this guy. So explicit invariance bilinear form. Bilinear form on YouTube. Okay, so strategy. Strategy is, first of all, we're going to exhibit V0 as a sub-representation. After that, I mean, this is sitting inside not S2 V2 star, but S2 V2. So we're going to use an intertwine. Okay, so we're going to create an intertwiner. Okay, from that tau intertwiner that we looked at in the first hour, we're going to induce an intertwiner from this space to this space, and then we're going to restrict to the image of this V0 sitting inside here. Okay, so let's make this all explicit and concrete. Okay, so let's do A first. Okay, so we are interested in this V0, this zero weight space sitting inside this S2 V2. From our table, see our table here, it's two-dimensional. Okay, so the zero weight space in S2 V2 as dimension 2. Okay. The general vector in here looks like what? So I'm using this this O dot with that denotes symmetric tensor product here. Okay. So let's consider x squared y squared like that, and xy. Okay. So
Sorry, if I can, quick question, just to
absolutely
make it clear for myself. So back in the table, we had this symmetric table, and you didn't bother to write down the lower triangular. Is this because if you think about the corresponding vectors that you drew in yellow in the previous table, if you're taking the products, you have symmetry in the product, and so
that's right. That's right.
Okay,
Yeah.
thank you.
Yeah. So for instance, you look at this guy here. Okay, so here, there we have. Oh, oops. Okay, x squared, xy, y squared over here, right? And x squared, xy, y squared over here. Okay, so if you think about where this zero comes from, it's the symmetric tensor product of x squared with y squared. So in my notation below, it's x squared O dot y squared. But that's the same vector as y squared O dot x squared. It's a symmetric vector. And so we don't want to double count that.
So could you say that in general that anything that gives you a symmetric table of eigenvalues, have this property here? That you don't really need to, you only need to concern yourself about the upper triangle, or you just need to write that down, and that gives
yeah. I mean, basically the upper triangle part. Yeah. Yeah, because
okay.
Otherwise you're double counting it, right? The stuff strictly below has a counterpart in the strictly above. Yeah. Those are mirrors.
Okay, thank you very much.
Yeah. Okay, so right. Notice that this guy This guy has weight 0, right? This has weight 2, this is weight minus 2, 2 plus minus 2 is 0. This is weight 0, this is weight 0, 0, 0. So certainly this is weight 0, this is weight 0. From our table before, we know that these are the space is two-dimensional, and so now we know that these guys are spanning this two-dimensional space. Okay, so we're going to put some undetermined coefficients in front. And then, yeah, so for this to span a trivial graph, we're going to require x on this W to equal to 0, okay, where x is this differential operator we went before. Differentiate y with respect to y, and then multiply by x. So 0, x on W, right? X acts as a derivation, right? You Leibniz rule. Okay, so on this x squared thing, okay, so x kills it. X squared is highest weight, right? So x kills it. So, but okay, let me just be explicit. And so x squared. X on y plus xy x. Okay. There is a symmetric tensor product over here, so actually this vector is the same as this vector. Okay. All right, so let's just evaluate this. Okay, so this is 0. This gives me that. And then for this guy over here, right? So you differentiate with respect to y, and then you stick an extra x in there. So you have mu and then x squared y, xy. But I have that again over here, so I'm just going to double count that now. Okay. I did something wrong. Okay, so let's just collect terms. So we have 2 lambda plus mu x squared. Now all this has to be the 0 vector, right? So this is telling us that mu is minus lambda. Okay, so lambda is arbitrary, right? And you should expect things not to be completely pinned down, right? Because we're creating a vector that's ultimately going to be an eigenvector. And once we have an eigenvector, well, we have an eigenspace, right? So the eigenspace is a vector space. So once I have a vector that's in there, I know that the line spanned by that is certainly also a line eigenvector. So therefore, well, let's take lambda to equal to 1, and we'll use this as our generator. Okay. Now we've only imposed that x on this W is equal to 0, right? Do we necessarily have that y on this W is equal to 0? Yes, right? This is a knowledge that we've gained from the theorem of highest weight, right? We have these representations Vm, where the eigenvalues are symmetrically arranged around 0, right? You have the highest one, m, that you lower by 2, lower by 2, lower by 2, all the way down to minus m. Okay? It's symmetrically arranged. It's a discrete symmetry. And again, that's something that's going to come up again later in a more general fashion. Okay, but just to convince yourself, go ahead and check that y. Let's look at B. Okay, so part B was to take this vector, which lives inside, right, S2 V2, but then apply an intertwiner. So we're getting over to S2 V2 star line. Okay, so how do we induce an intertwiner? Intertwiner from where to where? So S2 V2 to S2 V2 star. So this might be a little bit confusing when you first, like V2 itself is a symmetric tensor product. It's an S2 C2, right? So you're doing S2 of S2 C2. Okay, but so it all makes sense. Okay, just so that's why I'm not writing it out explicitly. So, okay, so we induce an intertwiner from tau previously. So recall tau sends x to partial y and y to minus partial x. Okay, so what we're going to do is we're going to induce it on these symmetric tensors. Okay, so you have, well, first of all, so we want to apply that to all this. We're going to apply it linearly, so we're going to apply it there and like apply it there. How am I going to apply it over here? I'm going to apply it on each factor. So tau over here, tau over there at the same time. Okay, not like a derivation, but at the same time. Okay, so apply it there and apply it there. How do I apply it over here, say? Well, I'm going to do it, in the way that you do it on symmetric tensor power. So tau of x squared is tau of x all squared. Okay. So use the definer from tau previously and apply it to W above. Okay, so W is getting sent to, this is what I'm going to call G. Okay, so X gets sent to partial Y. Okay, I'm going to apply it to X squared, so that's going to be sent to partial Y squared. Y squared, well, Y gets sent to minus partial X, but then I have to square it. So you're going to get partial X all squared. And then keep going. Okay, so over here, this minus sign will introduce a minus sign on this, but then it's going to get compensated by another minus sign, so those are going to cancel. So I just had this minus sign over here. Okay. All right. Good. So this is our expression for the bilinear form. Okay. Looks kind of weird, right? But I mean, it's right. This is defined on input vectors from V2. So I'm going to feed it symmetric, well, homogeneous polynomials in X and Y. Okay. So let's make this explicit. Okay. So in particular, the exercise now is going to be, okay, so let us interpret so-called null vectors. In V2. And in doing so, we have to make this G very explicit in terms of basis. Okay, so with respect to the basis given here, okay, we have G looking like this. Okay. What does this mean? I take this G and yeah, when I feed it x squared is 0. So that's this 0 over here. Okay. G x squared xy, well, that's also 0. That's this guy over here. G on x squared y squared. Okay, so as I want to get 2 here. Okay, I want to use this expression over here. So I'm feeding x squared in the first slot, y squared in the second slot. If it falls over here, right, I'm gonna differentiate twice, okay, once with respect to x, with respect to y, so it'll kill either of these two vectors. So if I feed it over there, it's just gonna be 0. Over here, there's a symmetric tensor product, okay, so I have to reverse the order. Yeah, sorry, actually just my convention for symmetric tensor product, okay, V O dot W. Here I am going to put a 1/2. Okay. Okay, so let's just see that this gives this coefficient over here. Okay. So this guy is up there like this. Okay. This is a symmetric tensor product. When I have the right, okay, let's just try that. Okay, so this is 1/2. Okay, so this guy will evaluate to 0 on that. So this is not going to give any contribution. Okay. Whereas this guy, right, is going to differentiate this twice. Okay, so that's going to produce a 2. This at the same time is going to produce a 2 on there. So 2 times 2 is 4, divided by this 2. This gives you a 2. When you input x, y, x, y, and this is et cetera, et cetera. Now, from this G that we have here, okay, we can also check that we have invariance directly. Okay. So we sometimes might be a little bit worried about the factors of the half, or whatever. We actually have the right answer that we have an invariant tensor. So we can also check invariance directly.
Sorry, so I
Yeah.
think somewhere I might have fallen off here. So you
Yeah.
wrote i.e. g of x squared y. Oh no, g of x squared. Never mind.
Yeah,
I realized
so
what I didn't.
spelling out what this means, right? So
Yeah.
we're working in this basis, and these are the components of this G in this basis. Okay, so as in this 0 means exactly this 0 means not, et cetera, et cetera. Okay. Okay, so we can also check invariance directly. Okay, so what does that mean? So A on G is equal to 0 for all A in SL2, sufficient to check it on the basis. What does the action on a symmetric binomial form mean? Right? So this is something that you guys discussed earlier on. So this means that A transpose G plus G A is equal to 0. Okay, so this is how you were used to thinking about it in the first month or so. Okay. Another way of expressing it is just A. This is the action on a symmetric binomial form. Okay, so I'm spelling this out here. Okay, so but what does this mean, right? Okay, because this is a 3x3 matrix. A, I have to express it as a 3x3 matrix. But we know what that is because because we could induce the action on V2. Okay. We've seen those matrices before, okay, in the basis that we're considering over here. So we're working in this basis as we have been doing before. So what are those matrices? Okay, so here, X is this, H is that, Y. Okay, so we have this 3x3 matrix, G, that is nice, a nice object to work with. As in, it satisfies this nice FL2 invariance property. Okay. So, yeah, but given any symmetric bilinear form, you could talk about all vectors that are null with respect to that bilinear form. Okay, so let's U. Okay, so let's take a general vector. I'm going to put a coefficient of 2 in here. Okay, so 2bxy. Okay, so this guy is in U2. Let U be G null. Okay, so what does that mean? It means that when I shove it into this G, okay, so I pair it with itself and shove it into G, then I get 0. Okay, so explicitly, what I'm doing is I should be taking the coefficients of 2b. I feed the basically feeding this into the bilinear form. Okay. So you carry out that matrix multiplication, and what you're going to get after collecting is 4 times AC minus B squared. Okay. So what is this expression? Right? That's the discriminant of this polynomial. Okay. I put this 2 there. So, oops. Okay, so this is the discriminant. Okay, which is a familiar and important object. We're going to what happens when this is 0. So this says that you have a multiplicity 2 root. Okay, but or phrased in this way, in this language over here with binary forms x. So I'm going to be using x, y. It says that U is a perfect square. Okay, so this is some linear polynomial. And there's some, yeah, there's special quadratics that are just perfect squares. Binôme vectors. So what we just produced out of this is this invariant tensor that's when you write it out in terms of polynomials, right, it's the discriminant, okay, this important object. But like you can imagine trying to do this in a more complicated situation, right? So what about on cubics? Okay. Can you find the expression for the discriminant there? Can you produce the tensor, right? So this discriminant here for quadratics, the coefficients are very familiar, but you know I can't remember the one for cubics, but this is one way of deriving it from scratch via representation via SL2. Okay. Questions before I move on? So let me phrase. So these are good examples to go through in detail, just get a feel of these computations. Okay, so some general results. So general results, and I won't give the proof, but like, yeah, it's a challenge. So I'm actually only proof it. Using the ideas that we've introduced today. So as SL2 representations. Okay, so let's go back to the question that motivated this section. So VM tensor VM, S2 VM, wedge 2 VM. What's the decomposition? Well, clearly it starts from the top weight. What's the top weight for this? It's M. What's the top weight for that? It's N. And then you add them. So the top one is clear. Okay. So the next question is what happens after this? So it turns out it's lowering by 2. And how far does that go? It's always lowering by 2 until you get to the absolute value of the difference between them. Okay. So this becomes a combinatorial sort of exercise. Okay. What about S2VM? Okay, well, the top one is clearly going to be 2M, V2M. Afterwards, it's a drop by 4. And drop by 4, etc., etc. Okay. Of course, you can't go in this coefficient, this subscript cannot go negative. Okay. So, yeah, you just keep going until you have no room left. What about this wedge 2? So the top one is 2M minus 2. Again, it's a drop by 4. Oops. Okay. So these are nice exercises to go through, and yeah, you see complexity as well as how combinatorics are just figure out what's happening with all these weights to identify each of these factors in the decomposition. Okay. So the next question we get asked with these decompositions, just linking up with what we just discussed, is there a V0 in there? Okay, this trivial representation, because that would correspond to an invariant tensor. Okay, so here's the statement. For each m greater than or equal to 0, okay, integer, the SL2C era VM admits an SL2C invariant bilinear pairing M that is symmetric or skew symmetric, okay, depending on the parity of M. So if M is even, then there's a symmetric gap. If M is odd, then it's and in fact, this is going to be unique up to scale. Okay, so we looked at the case M is equal to 2, and we found the symmetric invariant bilinear form, wrote it out explicitly. Okay. Right. Okay, so we have these nice invariant tensors. Yeah, for each M, sometimes it's skew, sometimes it's symmetric. Okay. Let me go back to this this Fletch-Gordon pairing business. And formulate the result in general. Okay, so I'm going to denote it by subscript P. Okay, so this is a map from, this is a projection Okay, from VM tensor Vn to M plus N minus 2P. Okay. So I've used this subscript notation. Yeah, so let's just make sure that this makes sense. Okay, so over here, VM tensor Vm, you have the top one and then lowering by 2. Okay. So this shift of the top one, so M plus N by multiples of 2. Okay, so these certainly appear in this decomposition. Right, so you could ask to do this projection. Okay. Also, is this consistent with this subscript M thing that I have over here? Okay, so here, let's see. Here. Yeah, so here we're talking about the case N is equal to M. Okay, and so I would have M plus N, so 2M, and then I'm putting P is equal to M, so minus 2M, so V0. So basically, I could view this guy as so a map from VM tensor VM to V0, which is what a bilinear point is, right? This is the trivial representation, the one-dimensional. Just another way of okay, so what do these guys look like in general? Because we have this picture in terms of polynomials here. Okay, so we can express this actually in terms of polynomials. So let F and G be like so. F here is in Vm, okay, homogeneous polynomial of degree M. This guy is of degree N. So what does this guy look like? The lovely formula here, okay, in terms of binomial coefficients. So what I'm going to do is I'm going to differentiate F P minus K times with respect to X, K times with respect to Y, and then the opposite for G. So K times with respect to X, P minus K times with respect to Y. And the results, and then multiply those two results together, right? Multiply those two together, take this linear combination, and the claim is that this is going to be M plus N minus 2. Okay, so this is symmetric polynomials in X and Y of degree M plus N minus 2P. Okay, so this is degree M, this is of degree N. Okay, I have differentiated a certain number of times, but yeah, P derivatives over here, P derivatives over there. Okay, everything, think about it, everything matches up so that you are going to be landing in this space. So these pairings are so-called SL2C equivariant. Okay. What does that mean? Okay. At the Lie algebra level, you have to apply things with a Leibniz rule. So A dot F in the first slot, keep the second slot the same. Then do the pairing. And then F A dot G, take the pairing. And then you have the output result, but the output result lands not in the trivial representation here, but in general, some irreducible representation. So there is an action of SL2. Okay, so that's what SL2 equivariance means.
So this kind of looks like a wannabe Leibniz rule, I guess.
Yeah. So let me just mention this next comment here. So equivalently, what this is saying on this tensor product space from over here. From there to there. Okay. This is an intertwiner. And the above can be written as how A dot V is a how V, where V is this tensor product. You're feeding this tensor product into this carrying. Okay, so F goes in the first slide, G goes in the second. Okay, but of course this action A dot V, A on this tensor product is via Leibniz. Yeah, this is what you're saying. So yeah, so just to underscore this formula here, okay, let's go back to this S2 V2 case. Okay. So let's write out the Klotz-Schwarzschild pairing. Okay, so right, we have this V4 and V0. So we have two pairings here. Okay, so we have FG0 is, well, in this case, we're not doing any differentiation. Okay, P is 0. So it's just straight up multiplication. And that's familiar, right? We saw that earlier, that we're just doing this multiplication on each of those terms that's appearing, and then of course everything is extended linearly. So those coefficients that we had in that table, we're going to add together on the right side to give what was on the left. Okay, what about the next one? So FG2. Okay, so this is landing. Yeah, it's going from V2 to V0. Okay, so if we write out the Klotz-Schwarzschild pairing in this case, let me just write it out explicitly. It's Fxx Gyy minus 2 xy Gxy plus Fyy Gxx. Okay, so you can check. This is multiple of what we wrote before. I won't use G here, I guess we just want to polynomial as G. Okay. So everything is going to be consistent here. Questions before I will do a couple more things. So yeah. Actually, let's get into time. So maybe this would be a good place to stop. Obviously,